Okay, so what we want to talk about now is vectors. And vectors, well, let me give you an idea of why we need vectors. If I said I walked 20 meters and then I walked 10 meters, how far away am I from where I started? Well, I could be 30 meters away if I walked 20 meters and then I continued in the same direction. I could be 10 meters away if I walked 20 meters out and 10 meters back. Or I could be, and let me put a little question mark next to each one of these, anywhere in between, because I could have walked 20 meters and then 10 meters this way. And we don't know what that ends up being, how far away I am. So what we need to do, and I've already started doing it, is we need to use things called vectors. And vectors are quantities with magnitude and direction. Magnitude just means size, amount. Examples are 50 meters, 20 meters per second, 8 newtons, 40 degrees. Direction, obviously you could use north, south, east, west, up, down, left, right. If we have a set of directions defined, if we have axes, for example, or a number line, you can use plus or minus. They're all possible directions. 50 degrees away from horizontal. So there are all sorts of different things we can use for direction. When I couple those two things, I have what's called a vector. Now sometimes you're going to see a vector, it doesn't have the direction explicitly defined, but you could say 50 meters. If I've already said that right is positive, positive 50 meters means 50 meters to the right. We'll see examples of that in the displacement discussion. Okay, so vectors. What are examples? Examples of vectors. Displacement, which is how far away you are from where you started, or how far away you are from the beginning of some time interval. And we'll talk about that in position. And velocity is an example of a vector. Okay, speed is a scalar. Let me put versus scalar. Scalar just has magnitude. We don't worry about the direction. So speed is a scalar. Velocity is a vector. Acceleration is a vector. Force. And there are others, fields and things like that. These confuse people. Displacement, velocity, acceleration, those are vectors. I think of them as the physicsy kind of things. Physicsy kind of quantities. Okay? Force obviously has a direction. It makes a big difference whether I push one direction or another direction. Okay, so those are example of vectors. Notation for vectors could be bold, or it could have an arrow. There are a few different varieties. Sometimes you'll see it in italics. But for the things that I'm going to do on paper, I can't really show bold. So for example, A could be a scalar, but A, and let me make it big, that could be a vector. You're going to see in some books like that. I don't like doing the bold, so what we use is arrow notation. A with a little arrow on top of it. Okay, and that arrow is always going to the right. It's just a notation. It's not, there's no specific meaning about the fact that we draw an arrow over there. Sometimes you'll see it with just a line over it. I like to use that for average, so let's not really worry about that. But a little arrow is a good thing to have. Okay, so that's where a vector, that's what a vector is. Now let's talk about how we use vectors, how we manipulate vectors. Okay, let's take this. Let's take I'm going to put A equals 20. I'm going to use newtons, force. Okay, so that vector has a force of 20 newtons, has a magnitude of 20 newtons, and it's in that direction, obviously. That's why we use arrows to portray vectors. So that's an example of a vector right there. One thing about vectors is I can move them anywhere. So for example, this one right there, that would be the same vector. That would be an equivalent vector. Okay, I can slide it around, I can move it here and there. That's one of the nice things about vectors. I'll say they're movable when we draw vectors. As long as you keep the same magnitude, in other words, the same size, and the same direction. And once you've established this, once you've drawn this for one vector, that you've set a scale. So right now on this, if this is another one, if I called this B, this would have to be, if I drew this right length, right around 20 newtons, because that length is 20 newtons. This length must be 20 newtons. So this force and this force are very different. They're going in the same direction, but they have a different magnitude or size. Okay? Now let's talk about how we manipulate these vectors. Okay, and one thing that we do is we multiply by scalar. Multiplication by a scalar. This is trivial. This is my vector. I'm going to call that A. Okay. This one, if I multiply it by, let's say 3, I would just multiply the size by 3. I'd keep the direction exactly the same. 3A. Okay, very easy. So if that's A, this is 3 times as big as A. So multiplied by a scalar. And once again, scalar is just, it can be a number, 3 in this case. It can be something with unit, but it doesn't have a direction. Okay? Negation. Negation, in other words, making something negative. Negation. Here's A. Well, let's just use the same A. If that's A, negative A just means times negative 1. And if you think of it on a number line, negative means going in the other direction. So I'd have to go, A was going in that direction, so negative A would be the same size, same magnitude, but in the negative direction. So very easy. Now we need to talk about addition. And addition can be a little bit confusing, but it doesn't have to be. Let's take 2 vectors. And one vector is going to be, I'll have A and B, okay? So here's A, and here's B. Okay? Now, A goes up and to the right, B goes down and maybe a tiny bit to the left. Okay? If these were displacements, or let's take forces, if I push up and to the right and somebody else pushes down a little bit, I would expect that the ups and the downs are going to cancel somewhat, but it's going to tend to go to the right. The net force is what we call the sum of the forces, is going to be mostly to the right. So always use that as a check of whether you're doing this addition correctly. The way you add is by addition is called tip to tail. And we say tip to tail. Let me write it over here. Tip to tail. Since we can move vectors, I'm just going to move one of them, take one of them and slide it over so the tip, so the tip of this one is at the tail of the other one. So I slide B, got to redraw it here with the same magnitude and the same direction that it had over on the other location. So all I did is slide that over. Okay, so it goes up, it goes down. The resultant, which is what we call the addition, A plus B in vector arithmetic, is just going to be, if I start here and I draw a line to the end. Here's my A plus B. Okay? So when you add, you're putting them so they make one complete path. So I say tip to tail, one continuous path. And then draw a resultant. So 1, put them tip to tail. 2, draw the resultant from beginning to end. So in other words, you don't go from here back to here. You go from the beginning where you started to the end. Think of it this way. If I told you to walk so many steps this direction, then so many steps this direction, you'd end up here. So if I wanted to minimize that, if I wanted to simplify that, I wouldn't say go from here to here. I'd say start here and go so many steps in that direction. And it would accomplish the same thing. Remember, when you're adding these two together, you're trying to find something, a resultant, that replaces all this stuff. So that's vector addition and just the basic concepts of vectors. In the next video, what we'll do is we'll talk about some other manipulations of vectors where we can break them down. For example, we don't always want to do it graphically. We want to be able to figure out numerically what A plus B, how far away it is in different directions.